Welcome back. This is part two of three. We're going to be covering slides 34 through 63. Um, let's dive in. Vertical turbine pumps, right? They are used out in the distribution system. However, we're primarily going to be focused on their application in wells. So you have your impellers that we're now familiar with, and those are mounted in called a bowl, or, commonly referred to as a bowl. And then that bowl is, positioned within a can. And so this is, positioned down at the water level, well below the water table. Um, the flow moves parallel to the shaft, not along the shaft, as it is pulled up out of the aquifer. Um, and those can be stacked, so you can create like a multi-stage uh, pump, and that's good for high heads and good efficiencies. Here we could see a cutaway of what it looks like inside of these vertical turbine pumps. You could see you've got the impeller down there. This one appears to have a closed impeller design, and and inside there, of course, you got the diffuser vanes, which send it out in a radial type of flow, right? So it's coming in from the sides, and then the flow is traveling at a right angle to that. So that would give it that radial flow. This slide, you could see the pump can, like I described earlier. It's got multiple stages here. So it's a multi-stage, you can see. And then you got your pump and motor, or the motor that sits above ground, obviously. And in this case, the discharges are above ground. Um, but this is kind of a cutaway and, of what a well typically looks like. Here you got the graphic that shows, how water flows in and then up. So as water is pulled in to that eye of the impeller, and then the diffuser vanes, discharge it through the bowl, and then up the can, right, and then up parallel to the shaft, and all that is being done by the power is coming from the motor up above ground. You have axial and mixed flow pump for this application. Um, but one of the big takeaways, for that is that there is high volume, low head, and it can handle water with solids. Um, so that's one of the advantages of using that style. In this image here, again, you got your pump inlet down at the bottom. You've got the propeller shaped impeller that brings the liquid up parallel to the shaft. And then in this case, the outlet pipe is below grade. This right here represents grade. And so everything that you see cut away and opened up here is below grade. But that's another way to design this well. Deep well applications, you're typically going to have a vertical turbine type pump. And so what you have is you got a motor that sits above grade and connects a long shaft down to your pump. And that shaft can be sometimes, 500 to 700 feet long. It could be extremely long. Some people, use wells at very deep applications just due to the limited availability of water. Now, if you've ever, worked on a main break or anything like that, you've had a hole full of water, you've probably used submersible pumps, and the the pump and the motor are basically connected right to each other, and you drop that down. It's kind of the same thing. You can have a similar application in deep wells too. So you can have something, that goes down a long shaft where you've got your pump and your motor down at the bottom, and then that pushes the water up. And then you've got a jet pump type that uses centrifugal force to force some water down at a high velocity, creating this vacuum that will then pull it out, or it's kind of like a straw effect, if you will, and pull, it's used to, push down to create the vacuum that's needed to pull the water up and out. So there's a lot of different ways to kind of skin that cat, if you will. Not that I promote violence to cats. Just turn of phrase. But yeah, there's a lot of different ways to accomplish deep well applications. In here, you've got, a nice little cutaway to show you what it would look like. You got a multiple stage. You could see the multiple different bowls that are inside of this can. You've got your cone type strainer that is filtering everything before it goes into the parallel sections of the vertical turbine here and pulls it up the pump casing and then discharges up at the top. So, and like I said, with the submersible pump here, you've got an electrical source that travels down to your pump or to your motor. And you can see the motor assemblies down here at the, below your pump actually. And you've got your inlet here. So, and then the multiple stages and, you know, that's the submersible pump style for a deep well installation. Here we have the advantages and disadvantages of your vertical turbine pumps. Yeah, you've got uniform flow, meaning like a constant speed and head, so you can have this constant flow of water until the water table drops to a point that you've used up and you need to let that aquifer recharge. The construction is fairly simple after drilling and dropping in the casing. Basically everything could be assembled above grade and then lowered down into this into the well. And then, of course, you can have multiple stages like we've talked about. And then you've got fairly high efficiency. Like, with the centrifugal pumps, it was down 75% to 85%. Here we're, 85 to 90%. However, I don't know that, you know, if you're really limited and this is your only option, this is probably the way you're going to go. I think the disadvantages kind of outweigh the advantages in this case, with the high initial cost, high cost of repair. You're very limited on your efficiencies just due to that narrow range, like I said, with the water table. And then your inability to pump any kind of solid matter here. If anything gets through, it might damage your pump. So I don't know that advantages outweigh the disadvantages ultimately. So now that we've talked about a lot of the different types of pumps, we're going to talk about the components that make up these pumps, right? So we've talked somewhat about impellers. So you should have some kind of an understanding there. You have wear rings, which are designed to wear down, because the cost to replace those is much less than if you have to repair other parts of your pump. So I'll show you where those are located, and we'll get into those a little bit. Obviously, there's the shaft and shaft sleeve. You've got packing glands, rings, mechanical seals, lantern rings, bearings, and couplings. So these are just some of the components of your pumps, and we'll talk about them a little bit more in depth here. First, let's talk about the wear rings, right? So these are going to be installed in between the running surfaces of the impeller and the housing that it's located in, right? Um, it obviously, like it says in the name, right? It's a wear ring. It's there to prevent excessive wear on the expensive impellers, right? So if you can design a weak point, like that makes sense, right? So you do have your impeller. Outside of that would be the wear ring, and then outside of that is your casing that holds it all together. So they are designed to deteriorate, but because of this, they do provide a pump efficiency or inefficiency, excuse me. It's just in the design. However, in the maintenance and cost of everything, it pencils out. Next, you have the shaft, right? These are usually going to be constructed of steel or stainless steel. Just depends on the cost that you're willing to put into these things. But then the shaft sleeve will be, constructed of like a bronze alloy, and it's used because if you would rather have that fail than the shaft itself. It's a lot easier to replace a shaft sleeve than it is the shaft itself. And then here in the image, if you look, you could see that there's the multiple impeller stages and how it's all kind of connected here. Now we have packing material, and it's going to be made of many different types of material. But what it does is that it, creates that seal between the wet side and the dry side. And just like any pump, you want to have like a little bit of a drip, or just a small flow that comes from these things, and that drip and that water is then used as a coolant to prevent the shaft from overheating and warping, and so the packing is installed inside what's called a stuffing box. And then the way that you would install this packing is that you want to stagger it, right? Which means that the ends of the packing are not going to be in alignment. You want to offset those. If you put them in alignment, there's a good chance that you will have a much bigger leak by than you really want. In this image, you can see that there's, the different types of packing glands that are available. And you would put them inside this stuffing box here, right? So it would all go down inside here, and then you would bolt this down in together to, uh, you know, create the seal, right? And so if you look here at this image on the bottom right, you could see the staggering of these packing glands. And that's kind of how you want to do it, about a quarter of a turn off from one another. And then here's a real picture of it. You could see that this was all placed inside of a stuffing box. Um, okay, so you have this shaft that is going from the motor and then into the pump, right? And so that's where these packing glands are going to be located. However, they can only withstand so much pressure. So typically, when you get to a point where the suction pressure is greater than 60 psi, you're going to want to use a mechanical seal instead. Those are much more rigid. They, just strength-wise can withstand the greater suction pressure. And so that's why, like with pumps, like we've said, you pump from a lower pressure to a higher pressure. And in a lot of cases, that lower pressure is, below that 60 psi. But when you do get to a point where you're greater than 60 psi, you're going to need something that will be able to withstand that pressure. And so that's why you use a mechanical seal at that point. Next, we have lantern rings. Now, these are going to be used when you have a suction lift scenario. So, if your water source is below your pump, that's considered suction lift. And what can happen is that a vacuum is created because you're trying to pull water up, right? And if you have air in your line when you're trying to pull something up, you can never achieve that vacuum. So what a lantern ring does then is it prevents air from entering into the casing and ruining your suction or your vacuum you case here. Um, so they're installed again inside that stuffing box like we've talked about, and their purpose is to allow water to escape but seal against air. And of course, we know that the water that's escaping is used to lubricate the shaft and reduce that heat friction. So lantern rings allow water to escape but prevent air from entering. So here you can see a cutaway of what that would look like. You've got your stuffing box here, and inside of it, you've got your packing that's been installed. You've got your shaft, and then right there in the middle is where that lantern ring is located. So if you think back to that image a couple slides ago, you had a couple pieces of graphite packing on each side of that ring, and that ring is that lantern ring. Um, yeah, there's a nice little cutaway. Hopefully that it helps clear up anything I've said so far. Okay, here we got bearings. So anytime a pump is started, you've got like a thrust that's happening as that motor is turning over so quickly. And in that thrust, you can have what's called a moment movement, where the shaft would want to move, eh, in a different direction than what it's oriented. And so you've got these bearings that are there to help guide and support the shaft to prevent that moment movement. Um, and so uh, that's essentially their purpose. Anyone who's ever been inside of a pump house when those pumps turn off, you can typically hear these bearings as the pump is winding down. It sounds like horrible cavitation, um, but that is the purpose of your bearings. The last thing we're going to talk about as far as components go is the coupling. The coupling is just what's going to connect your motor to your pump. There's many different ways to do that, but in this image here, you can see that, it's just a coupling. A coupling is just one way of connecting two different shafts. In this case, couplings are used all over the industry in many different fashions. But yeah, a coupling is just what's going to connect your pump to your motor. So, like everything else in the industry, anytime you're working around a pump and motor, safety is obviously going to be a big concern, right? A lot of people get hurt around these pumps without taking the proper procedures. And so those proper procedures, are going to be right in line with our lockout tagout procedure. And so you need to be familiar with that and ensure that that is in place before working on or around any type of pump. So you want to make sure that the circuit or the electrical energy is physically disconnected and locked out, right? Some kind of a locking mechanism device that would prevent accidental reconnection of that. You want to be sure that um, the lockout has the operator's name, date, and the reason for the lockout. If there's supposed to be multiple on there, making sure that um, those are all in place, and then only the operator who installed it should be the one to remove it. And then once it is uh, tagged back in service, it's a good idea, or excuse me, once it's tagged out of service, it's a good idea to try and turn the pump on just to ensure that the steps that you took actually worked. In the pump operation, the impeller must be submerged prior to starting. However, that will not always be the case. You won't always have a positive suction head, meaning you'll have several feet above the pump where you're drawing your source from. So in this case, you have to have what's known as a foot valve, and then that will be, you have that foot valve that's going to hold that water in the pump, and then you have to prime that pump. And so you can see by these images down below that you've got a priming port, which is used to bleed the air out, or you're pouring water in to fill up the pump case with water, which is going to, when it starts, then create that suction to be able to pull the water from below the pump. So that's kind of how priming works. So yeah, if you look at these images here, in the first one on the left, you've got air inside of your pump, and you're not going to be able to create that suction there. So you have to fill it full of water, and then once you turn that on, it'll be able to then create that vacuum to be able to lift that water up. Just in case I didn't describe it well enough, or you need another image to help you understand the difference between suction lift and suction head. Here on the image on the left, you can see you're having to lift that water up, right? So if your pump is above your water source, and so you have to create that suction lift. Whereas the image on the right, you have suction head. So you've got a water source that sits higher than the suction side of your pump. And so that there's the difference in case I haven't explained it well enough. Like I've said before, a foot valve can be installed at the bottom of the line or the beginning of the line. And all it is a check valve. It's just there to hold that water in the line, which can help maintain its prime. So if you're having issues, priming your pump, installing a simple check valve can help eliminate those issues. Um, and then, better situation would be, yeah, you locate your water or your pump so that the water source is above the pump center line, and create that suction head scenario. So you always want to start against a closed valve to prevent water hammer and surges. However, like I said before at the beginning of this lecture, on part one, is that if you have a positive displacement pump, you don't want to do that because you can create overpressurization. However, in most other cases, you do want to start against that closed valve to prevent that water hammer or the pressure surges. So then you have these pump control valves that are, going to be installed just downstream of the pump. And as that pump turns on and increases pressure, it's going to, in a way, push open that valve before allowing water out into the system. However, you don't, if the last thing you want to do is to throttle a discharge valve while it's working. Um, a typical gate valve or something is not obviously going to work. You can damage that gate valve much quicker than you would like a globe valve or some kind of diaphragm valve. So yeah, just in general, you're starting pumps against a closed valve to prevent water hammer and surges. One condition that can exist during pumping operations is known as cavitation. And cavitation is air that gets inside of your pump and basically explodes against the sidewalls of your impeller. Um, and it can damage your pump over time. It leads to pitting, and then once you take off that outer coating, it can lead to corrosion. But cavitation occurs when suction pressure drops below atmospheric. So, yeah, you're most likely going to see this happen in a suction lift type scenario. Um, it can happen in a suction head scenario if your water level drops, too low, which is why you want to have, some kind of a level sensor cutout that will turn off your pump, if a water level gets to a certain point to prevent that from happening. But it can seriously damage your impellers, and yeah, it sounds like rattling marbles inside of your pump. So in the images here, you can see the solid blue that has sufficient available pressure or lack of oxygen or air in the line. And then in the next image, you have that that low available pressure and air getting into there, which is going to create the pitting, as you can see on this image of the impeller that experienced cavitation. Okay, I put these on here because it's a good chance you're going to see them again, right? Always start pumps with the discharge valve closed, right? So I know I've talked about displacement pumps and how that you don't want to do that, but if asked on a distribution exam or in my class, if there's a question on there that says, do you start the pump with it open, the valve or the discharge valve open or closed, choose closed. Reason why? Because you want to avoid water hammer or pressure surges. So if you experience or see those kinds of questions, this is how I want you to answer. Okay, we can get into the semantics and the details of it if you'd like, but to assist you guys in your test, answer this way, please. And then, of course, you want to slowly close the discharge valve when the pump is shutting off, right? You can create water hammer in the other direction. Um, so as slowly as you open it when starting the pump, you want to do the same when turning it off. Another condition that can happen is pump vibration, and you definitely want to make sure that you're monitoring something like that. Again, it'll lead to a worn shaft, worn bearings, right? Um, and then if you have imbalance or misalignment, you can really damage your pump and motor. So being, cognizant of, vibrations on pump. And a lot of times when you're doing pump inspections, it's as simple as just putting, the back of your hand on the motor to feel for this stuff. When I was an operator going around making, doing pump and plant station checks, that was just a simple thing I did. I would just place the back of my hand on the motor and feel for that vibration. And so you've learned in time and experience what is normal and what is abnormal, and that's how you can monitor that. If your agency has money to spend, you can actually get a laser shaft alignment kit, and it will measure that for you. So you've got the different types of alignment, which is possible that you will see a question on that. You can have an angular alignment in which the where the coupling is offset. It's not aligned properly. You can have an offset. Again, these are all different ways that it's not aligned properly, or there's a combination of both, right? There's an offset, there's an angular alignment or misalignment, or there's a combination of both, right? They can all be really bad for the pump and the motor, and it might lead to other problems. So pump alignment is crucial. So anytime you're operating pump, it's typically controlled by some kind of a variable out in your distribution system. That may be tank levels or it may be pressures. Pumps will come on and satisfy the tank level, or it'll meet system pressures before dropping down, right? So we didn't really touch on it, but there is the variable frequency drive pump that will slowly ramp up and slowly drop down as it meets pressures, out in the distribution system. But then you've got pumps that, are basically all or nothing, right? They have one speed that they pump at, and those are usually used for filling reservoirs. And they typically flow at a much higher rate than your typical variable frequency drive pump. Um, but as tank levels drop or system pressures drops, more pumps can be, called on to run. So you can have multiple pumps operating at the same time. And then as you get closer to your goals, some of those pumps might drop off until one pump is running. And then once that last pump meets that demand, it drops off. Or it doesn't meet your demand, things drop back down, and you have more pumps turned on to help get you there. Um, so with that, that is the last slide of this lecture. Hope you're getting something out of this, and I'll see you on the next one.